Hello everyone, welcome to Tech Talk with Dave. Today we're going to talk a little bit about fiber optics, and we're going to just a very basic lesson in fiber optic technology, as it's one of the OSI model PHY types that we're running into more and more often. All right, so let's have a short little primer here on fiber optics. A fiber optics cable consists of three parts. It has a core. It's a glass center where the fiber travels. This glass center is doped with silicone, and each of the fiber optic manufacturers, they generally have a secret formula that they use to draw this fiber out of a block of the silicone and glass. Then on top of the core, there is a cladding, which is an outer optical material that surrounds the core. This cladding has a different refractive index than the core. And at the boundary between the core and the cladding, the light is held in the core by this difference in refractive index. We can see the effect of refractive index if you had a pencil or a stick in a glass of water and it's at an angle. You look through it at an angle and you can see it looks like the pencil is actually in two pieces. So that's the same effect that is going on within the fiber optic cable to keep the light within the core. And then on top of that, then we have the sheathing that protects the fiber itself, and then on top of that we might have armor, we might have multiple layers of different sheaths, and so on and so forth. And typically inside a fiber optic cable itself, there's never just a fiber. There's usually multiple fibers within the sheath. And so then, depending on what we're using the fiber optic for, determines what the construction of the fiber cable actually is. So if you've ever seen the process of creating a fiber optic cable, it's very, very cool. It starts off as a specially constructed block of glass, and then the glass is heated, and the fiber is drawn out of the center of this glass, and it's just drawn tighter and tighter and tighter to get it smaller and smaller and smaller until finally it's the dimensions that it needs to be. Of course, the fiber cable itself is very fragile, and so then the core and the cladding and the sheath and the armor and whatever else are added in order to take and make this fiber cable much more durable. There's a few different modes of cable itself. If we have fiber optic patch cords, for example, going in between devices within our data center, we might use multi-mode fiber optic cable for that. A couple of different ways that it's made. I'm not going to get into what the difference is, but there's a step index, there's a graded index cable, and typically we can use these cables in lengths up to about 1,000 meters, about 1 kilometer. Typically, they're multi-mode cables are much shorter than that, and they use a large core, 50 to 60 microns, and the reason it's called multi-mode is that there are many ways the light can travel from one end to the other. Again, but it still reflects off of the cladding, which is a different refractive index, as I mentioned before, and so the light does stay inside the multi-mode cable, but the distance that we can go is determined by how we can recover that fiber optic signal at the other end. So typically for multi-mode cable, 1,000 meters is the maximum. More typically, devices will have a specification limit of 1,000 feet, like 300 meters, and so that's pretty normal, and they're normally orange in color. Single mode cable now, this is how we go from a great distance, up to 100 kilometers or more, with a very small core, 8 or 9 microns, And the laser has only one way to travel down the core. There is no reflecting that goes on. The cladding holds the light within the cable as it goes around corners and bends, that kind of thing. And but there's still only one mode for the light to travel from one end to the other, laser to travel from one end to the other. Typically, multi-mode cable is at the bottom end of visible light. Single mode cable is almost never visible. You can't see the fact that it's on. Sometimes in a multi-mode cable you can see the fact it's connected just by the end of the connector is got a little orange or a red glow to it. Kind of interesting. In the early days of fiber optics, we used to troubleshoot multi-mode cable with a flashlight. So we could shine the flashlight into one end of the cable, and you can see of course, the light at the other end, and so then you knew you had a connection from this pair to this pair. So here's some typical fiber cable types. Single mode patch cables, often yellow. Multi-mode patch cables are often blue. Outdoor cables are armored and sometimes water resistant. They'll use grease, or they'll use ribbon on the cable to keep the water out of the cable. Fibers are color coded. Outdoor cables are bound in bundles of 12 fibers each. The bundles are grouped together in the armored, ultraviolet protected, water protected jacket, and oftentimes a steel or a nylon messenger cable is located in the center of the bundle for strength. And again, a lot of effort is taken with fiber optics in order to take and guarantee the robustness of the cable. When we work with the fiber strands that are connected together, the act of cutting them straight is called cleaving, and splices are done with automatic fusion machines that you take. The fusion machine will have the cleaver on board. You take and you cleave the cable, and then slide the two strands into either side of the machine, and the fusion splicer will take and line them up. Oftentimes before it splices, it'll take and let you on the little view screen that it has. It'll let you see what this splice might look like before it makes it, and then it heats the cable up momentarily, and the strands are then joined together. And the better the cleave, the better the splice is going to be. Oftentimes, you can get a splice that is better than 1/10 of a dB of loss through that splice. You test a fiber optic cable with a device called an optical time domain reflectometer, OTDR. You'll see the abbreviation. And what it does is it sends a pulse of light at the correct wavelength down the cable itself, and any anomaly in the cable will take and reflect some of that light or laser back to the OTDR. So what the OTDR does is it knows by time how long the pulse has been sent down the cable and returns. It knows how many meters or how many feet that anomaly is from it, and so it will take and draw you a graph or a map of the strand that it sees, and you can take then and determine where I have an open, if it's at the end, if I can see the end of the cable or not, or if I have a bad splice, a high loss splice in the way, whatever the case happens to be. Can't really do much troubleshooting on a fiber system without an OTDR. The strands are organized into splice trays within a splice housing. And so the job of the cable splicer is to take, of course, and splice the strands together according to the design plan, and then organize the cables. As you can see there in the bottom left-hand corner of the slide, we see a group of splice trays that are together, that are loaded up with strands that have been spliced together, and makes for a very, very neat outside plant system. On the right here, we see a patch panel that's in a data center, and he's of course using an OTDR to test one of the connections, one of the strands that are connected to the patch panel itself, and away you go. Sometimes we purchase the patch and the jumper cables that have factory installed connectors on either end. They normally come with a certification of the loss of the cable itself. Sometimes they do, sometimes they don't, depending on the manufacturer of the patch cable. And we can take and know the quality of the connection by, again, we test it with the OTDR. Now there's many, many different fiber optic connectors depending on the system it is that you're using. They can be single strand connectors, dual strand connectors, or multiples these days, multiple ribbon connectors. And so there are various sizes, various strand densities, and equipment that we use determine the type of cable that we need to connect to it. LC connectors are the most common today. That's the one that's circled in the green, and most SFPs use LC connectors, a pair of LC connectors together. So when we interface to fiber optics, the density, how many connections we actually need, can determine what it is that we're going to use as the interface for the system. In most cases, we're talking about a pair of connectors. Maybe the pair is, maybe we're going to repeat it 8 times or 16 times or whatever it is. So on a switch, we might have anywhere from 2 to 32 SFP interfaces. Plug an SFP in, plug the fiber into the SFP with the LC connectors, and away we go. But in data center world, we might need much more density than that. And so we have up to 25 fiber pairs can be located in a single connectorized interface. So there's many, many different ways of using the fiber optic cable. In the broadband world that we live in, by and large, if we're going to use fiber optics to connect from a switch or a router inside our building or cabinet at the base of the tower up to the tower, we're going to have an SFP in that switch. We're going to have another SFP that's in the radio device that's up the tower, and then we're going to have a single pair connection that goes between the two SFPs. Maybe it's bound in a cable with other pairs of fiber connections for more devices up the tower, and of course it may be shielded and UV protected and all those things. So a tower fiber system, fiber to the antenna. Whenever you see the FTT, that's fiber to the, and then whatever the last letter is, H would be the fiber to the home. Fiber FTTP is fiber to the premise. The many different ways the acronym is displayed. In our case, fiber to the antenna, I want to talk about just for a minute. Systems often include DC power cabling, maybe sometimes category 5 or category 6 twisted pair cabling, and single mode or multi-mode fiber optics. And generally speaking, the hybrid cable manufacturers that build these cables will build you cable to your specifications that you need if you're going to order a significant quantity of it. Typically, these days, cables include DC power and single mode fiber. That's by far the most common. And so we have a junction of some sort that's at the building at the base of the tower. We run the hybrid cable up the tower. The hybrid cabling will have the DC polarities and positive and negative, as well as the fiber cables themselves that come up to a probably a surge protected junction box that's at the top of the tower. The fiber is broken out, and patch cords are used to connect the hybrid cable to the radio device that's up the tower itself. And of course, DC power is then a DC jumper that goes from that junction box to the power connectors on the radio. This sounds complicated, but it's really once you've developed the system, it's pretty easy to replicate on various sites. The only variable really that you have in this is the length of the hybrid cable from the building, up the tower to the device, as towers can be different heights. All right, as usual, we welcome your feedback, your comments, any new topic suggestions. We appreciate an email to marketing@mbsiwave.com, and who knows, maybe your suggestion is going to be in the next Tech Talk. Bye for now.